Okay, here we are at the last section for this semester, section 5.3, linear programming in 2 dimensions, a geometric approach. So, what do we want to do? Oops. We move back out of red ink, back to blue ink, black ink actually. Black ink, go. Use to maximize, or minimize. Usually we're maximizing things though. Something in the form p equals ax plus by over a feasibility region. And what does all that mean? Well, P, usually this is a profit, and a feasibility region means that we have some kind of budgets, and we need to be able to maximize the profit that we want to make, given the budget constraints that we have to work on. So as an example, consider the inequalities x plus 4y less than or equal to 16, 5x plus y less than or equal to 15, x greater than or equal to 0, y greater than or equal to 0. So that's a set of constraints. We know how to graph these things now. We know that this is whatever's going on is in the first quadrant. Here are 2 lines. You graph the 2 lines. You find out which side to shade, and that gives you something, some region in the plane. These can be taken as constraints. We are making x number of things and y number of things. We have some constraints, right? A budget, we can use 16 of x and y in this combination and 15 of x and y in that combination. And we want to maximize some profit. Right? We're selling x's and y, we get $8 for each x thing and $B for each y thing. If this is our budget, and this is how we maximize things, as a profit function, how can we maximize the profit function? So, this is a graph of my inequalities. Right, that's in the first quadrant, that's the greater than or equal to 0, logarithm of 0. This region, let's go back to red for a minute, is often called the feasibility region. It represents combinations of x's and y's that I can actually make that are within my budget. I want to know which combinations inside this region will actually get me the maximum profit. And note that there are 4 corner points here. There, that's 3, 0. Here, 0, 0. Here is 4. Oops. 0, 4. And then there's this point. And what's that? Well, how to find a point of intersection? Usually it's fastest if you match coefficients. So what I want to do is look at these 2 equations and say, well, if I multiply the top one by 5, then I'll match the coefficients on x. And then it'll give me 5x plus 20y equals 80, and the second equation remains unchanged. Right? So, now I've matched the coefficients on x, so we just subtract these 2. What do we get? 5x minus 5x is 0x, 20x minus 1y is 19y, 80 minus 15 is 65. And that tells me what y is. And then I want to know, well, what's x? Well, I can just plug it in. And it doesn't matter which one of these I plug it into. I'll plug it into this one. So, boop. X plus 4 times 65 over 19 equals 16. Right? So it's just plugging in this y value for y, and if you actually solve that out for x, you get x equals 44 over 19. So what these two numbers are the x and y coordinate of our last point. So this intersection is 44 over 19, which is a little more than 2, and 65 over 19, which is a little more than 3, I guess. So y is a little more than 3, x is a little more than 2. So now I know the 4 corner points of my feasibility region. Okay, why do I care about the 4 corner points of my feasibility region? Well, suppose that the function I'm trying to make a profit of, ooh, my pictures go way down there. Okay. So we have this feasibility region P, and we can think of the profit as x plus y. Find maximum value. So what's the maximum of x plus y over this region, right? So if I pick any particular point, like that point, that's 1, 1, that would give me a profit of 2, because x plus y is 2. If I pick the point x equals 2, y equals 1, then that profit would be 2 plus 1, that's 3. So I can make at least 3. So, if we want to see what the maximum is, we can say, well, we'll plot 4 equals x plus y. Is it possible for me to make a profit of 4 in this region? And try plotting 7 equals x plus y. So here's 7. It's a different value p. Is it possible for me to make 7? Note one thing here. These are parallel lines. They've got the same coefficient on x and y, and that's what the slope is. It's just the ratio of the coefficients of x and y. They have different y-intercepts, right? They form the 7 share the y-intercept. So, if we look at our feasibility regions, this is x plus y equals 4. So you can think of this as, this is a profit line, or profit equals 4. Every combination x and y along here is a combination of x's and y's that will make me exactly $4 in profit. And there's a lot of values, we'll go back to red for a moment. There's lots of values that will give me exactly $4 in profit. But one thing we know about lines is that one side of a line is a greater than side and one side is a less than side. This direction, profit is greater than 4. This direction, profit is less than 4, right? 0, 0, for example, is on the less than side. So there are lots of places here where I can make a profit bigger than 4. Now this line is what happens if you get profit equals to 7, right? Or x plus y equals 7. That's out here. I can't make $7 worth of profit, because to be able to make that, I need to be able to make, say, 4 and 4.5. Well, 4 and 3. For example, and I can't make that because I've got too many constraints. I can only make combinations that are in here. So, I can make more than 4, but I can't make more than 7. This is the profit less than 7. So my profit has to be between 4 and 7. So, these are parallel. If I increase the profit from 4 to 7, what happens to this line? Well, getting bigger means moving it up this way. So let's see if this works. There. So here it is. We start at p equals 4, and it moves up to 7. Look at this GIF. There, right here. This is the last possible place that the line touches in the feasibility region before it leaves the feasibility region. That's where my maximum would be. So, line of increasing profit, they're all parallel. We get a maximum profit right there. And Let's get too much space there. So there it is. There's my maximum profit line that goes right through the corner. Profit here is, well, profit is generally defined as x plus y. We know it goes through the point x equals 44 over 19, y equals 65 over 19. So if we plug those in for x and y, this line is the profit. P equals 109 over 19. Right, there we go. So, in looking at this, right, this is $4 profit. We can make more than that. This is $7 profit. We can't make that much. Right here, right at that corner, that's where we get the maximum profit, 109 over 19, which is a little more than 5. So, does this happen all the time? Well, if we pick a different profit function, where's the maximum? And you'd think, okay, well, it's going to be some kind of thing, right? We have some profit function. Profit function will give us a collection of parallel lines with increasing profit moving up to the right. And so would maximum profit be here? Well, we must be a little bit careful about that. Here's the profit line for profit being 5x plus y. And notice that the last point it touches is actually the one down here. So the profit is going to occur, oops, we don't want this thing. The profit is actually going to occur at one of the corner points, but we don't know which one. Right? It might be this one, it might be that one, it might have been that one. So, what does this tell us? We have a bounded feasibility region. Maximum minimum of ax plus by occurs at a corner point. Okay. So now we'll do two examples of how to maximize and minimize things. These are a little bit lengthy, but they should cover all the stuff in 5.3, and again, most of this will be done in 5.1 and 5.2. So, here's a problem. Find maximum and minimum of P equals 4x plus 3y over the region defined by these inequalities, 2x plus 3y greater than or equal to 30, and that's a 3. 2x plus y less than or equal to 20. And 2x plus 5y greater than or equal to 34. With the non-negative restrictions, x, y greater than or equal to 0. That means we're in the first quadrant. Okay, how to do this? Steps, 3 steps. First step, graph the inequalities. Second step, find the relevant corner points. Third step, plug corner points. Oops, corner points into P. So, how do you graph inequalities? Well, we've been doing that for a couple of days now. So, step 1, graph inequalities. And for each one of my lines, I need intercepts and test points. So A, 2x plus 3y greater than or equal to 30. X-intercept is 30 divided by 2 is 15. Y-intercept, 30 divided by 3 is y equals 10. So there's my intercepts. Test point is 0, 0. If I plug that into here, this is a greater than, I get 2 times 0 plus 3 times 0 greater than or equal to 30, question mark. 0, is that greater than or equal to 30? No, that's false. Shade the side of the line the origin is not on, because this is false. So, second equation in our inequalities is 2x plus y is less than or equal to 20. What's my x-intercept? 20 divided by 2, x equals 10. What's my y-intercept? 20 divided by 1 is the coefficient of y here, so it's just y equals 20. And if we plug in 0, 0 as my test point, we get 2 times 0 plus 0 less than or equal to 20, question mark, true. Shade the side 0, 0 is on. So if I get true, then I shade the side the test point is on. If I get false, I shade the side the test point is not on. Okay, and then the last one is C, 2x plus 5y greater than or equal to 34. What's my x-intercept? Well, 34 divided by 2 is 17. My y-intercept, y equals, 34 divided by 5, that's 6.8. And again, our test point is 0, 0. 2 times 0 plus 5 times 0 greater than or equal to 34, question mark? False. Shade this side, our test point 0, 0 is not on. And all of this, remember our inequalities only in the first quadrant. So we need to graph this sucker. It'll just be in the first quadrant, and again, not in art class. Not really worried about proportions too much, just want to make sure that I get everything in the right order. So our first line A, x-intercept is 15, and we'll put that here. Y-intercept is 10, and we'll put that there. And so it looks like that. And we will label this one, 2x plus 3y equals 30, that's this equation. And clearly I didn't give myself enough space. Just seems to be endemic to these problems. So that's the big word problem that we'll do. And we want to shade, we'll put in some red arrows here. The side 0, 0 is not on, so we're interested in this side of that line. Okay, now x-intercept is 10 here for this line, y-intercept is 20. And that's 2x plus y equals 20, and we want the side 0, 0 is on for that one. So, blank, we want that side. So, right now, when this area that's possible is here, that's the only side that's on the right side of both. So, but we have this third line, where the x-intercept is 17, which we'll put out here somewhere. Y-intercept is 34 over 5, that's about 6.8, so it's less than 10, so it goes there, and that's this line. And so this is 2x plus 5y equals 34. Okay, great, and we want the side that 0, 0 is not on. So a little bit complicated looking graph, but this area here meets all of our requirements. It's on the correct side of this line, which is over here. It's on the correct side of this line out here, and it's on the correct side of this line out there. So this is our feasibility region. And what are the corner points? Well, there's one there, and one there, and this is the intersection of this line, which is 2x plus y equals 20, and of this line, which is 2x plus 3y equals 30. So, we've graphed it, we found the feasibility region, we found what the three possible corner points are. Step 2, find coordinates of corner points. We know two of them, because there's just these y-intercepts, we just need to find that one. So, 2x plus y equals 20, 2x plus 3y equals 30. So if we subtract the top one from the bottom, 2x minus 2x is 0x, 3y minus y is 2y, 30 minus 20 is 10, so y equals 5. And then if we plug y equals 5 back into here, say, we get 2x plus 5 equals 20, or x equals 15 over 2. And so that tells us what our three corner points are. I'm going to insert a little more space. Let me see, a little bit touchy sometimes. There we go. Okay, so corner points. We'll create something called a corner point table, which means you start with the three, in this case three, there can be only 3 corner points. 3 corner points, and what do we want for each corner point? We want an x and a y. One corner point is here, right? It's 0, 20, one corner point is there. This one is 0, 10. So x equals 0, y equals 20 is 1, x equals 0, y equals 10 is another. And then the last corner point was x equals 15 halves, y equals 5. So those are corner points. Our function that we're trying to maximize and minimize, way back up in the top, is 4x plus 3y. So we just plug these coordinates into this function and see what we get. If x equals 0 and y equals 20, then p is equal to 60. If x equals 0 and y equals 10, then p is equal to 30. And if x is 15 halves, then 4 times 15 halves is 30, plus 3 times 5 is 15, so 45. This is the maximum, and that's the minimum. So, we're done. This is our region. If we want to find the maximum biggest that this can be over that region, the biggest it can be is here, and the smallest it can be is there. And that's pretty much it. Now, looking at our giant word problem here, becomes a question of, well, how do we go from this huge word problem to using using the graphing techniques to be able to answer it. So, because of the new federal regulations on pollution, the chemical plant now has to use a new, more expensive process to supplement or replace an older process making some kind of chemical. The older process emits 20 grams of sulfur dioxide, 40 grams of particulate matter, and particulate matter just means dust, sort of little pieces of things. The new process emits 5 grams of sulfur dioxide, 20 grams of particulate matter for each gallon of the chemical produced. 60 cents on the old process, 20 cents on the new process is your profit. And you can emit no more than 16,000 grams of sulfur dioxide and 45,000 grams of particulate matter. So how many gallons of each should be produced to maximize the daily profit? So this factory can do, it's got 2 ways to make the same chemical, an old way and a new way. Both of them produce sulfur dioxide and particulate matter, but at different rates. Both of them provide a profit, but again at different rates. And you have restrictions on how much sulfur dioxide and how much particulate matter you can use. And So what should you do? Should you make all new stuff? Should you make all old stuff? Should you make a combination of the two? So, solving word problem. Part A. Define your variables. Let's do a little red here. How many gallons of the chemical should be produced by each process? Right? That's what we're looking for. So X gallons produced by old process, Y gallons produced by new process. These kind of statements are really used for when you're doing word problems. Literally write down what you mean by your variable. X equals, and then a sentence saying what X is, right? X is measured in gallons, Y is measured in gallons. Okay, so now we have to find our variables. B, figure out your inequalities. So, we're going to set up a little table because we need to know about the old process and the new process. We say, okay, what's your variable? The variable is X for the old, Y for the new. What do we know about it? Well, sulfur dioxide, which is SO2. The old one emits 20 grams. The new one emits 40 grams. No, the new one emits 5 grams. Particulate matter, we'll say PM. The old one emits 40 grams. The new one emits 20 grams. Great. Then of course we have totals. You can't have more than 16,000 grams of sulfur dioxide, and you can't have more than 45,000 grams of particulate matter. And then there's also the last step is the profit, 60 cents in the old, 20 cents in the new. And what we want to do is maximize the total profit. Great, so there's a little table, and now we can figure out our inequalities. The total amount of sulfur dioxide has to be less than or equal to 16,000. How much sulfur dioxide do we have? So we have a sulfur dioxide constraint. 20 times X is how much grams of sulfur dioxide I'm making in the old process, plus 5 times Y. That's how many grams of sulfur dioxide there is in the new process. That has to be less than or equal to 16,000. Particulate matter, 40X plus 20Y has to be less than or equal to 45,000. Right. So there's two constraints. Unstated, but assumed, is that we are actually making stuff. So Y greater than 0, X greater than 0. And what's I need to maximize? Well, 60 times X is my profit from the old stuff. 20 times Y is my profit from the new stuff. Two constraints, non-negative constraints, thing that I'm trying to profit. So how do we solve a problem like this? 3 steps. So what am I showing? I'm at C. Graph. D. Find corner points. And then A, B, C, D, E. Find the maximum using a corner point table. So, graphing. It's the same as we did before. For the SO2 line, that's my x-intercept. That's 16,000 divided by 20, which is 800. Y-intercept, 16,000 divided by 5, which is 3,200. 20 times 0 plus 5 times 0 is less than or equal to 16,000. Little question mark. True. So we graph the side 0, 0 is on. For particulate matter, x-intercept is 45,000 divided by 40, which is 1125. Y-intercept, 45,000 divided by 20, which is 2250. I'm plugging in our test point 0, so 40 times 0 plus 20 times 0, and I'm plugging into this equation. Is that less than or equal to 45,000? And that's true. So we fill in the side that 0, 0 is on. Okay, so now we can do our graph. We have 800, 3200. That's my sulfur dioxide constraint. And then we have 1125, 2250. That's my particulate matter constraint. We're required to be in the first quadrant. So this is our feasibility region. What are the corner points of our feasibility region? There's one there, there's one there, there's one there, and there's the one there. So, you can find the coordinates of this point, and it turns out to be x equals 475, y equals 1300. And again, that's finding the point of intersection of these two lines. Take this top row and multiply by 2, and then you can get rid of the x's and solve for y. Great. So let's find corner points. And last, set up corner point table. So what's a corner point table? We list all our corner points. There's 4 of them. This one is 0, 0. This one is x equals 0, y equals 2250. This one is x equals 800, y equals 0. And then the last corner point is that one, 475, 1300. That's our profit function. This is what we try to maximize, 60x plus 20y. So, if we plug in x equals 0, y equals 0, you get no profit if you make nothing. That's nice because, you make things make sense. If we plug in x equals 0 and y equals 2250 into here, we get 45,000. Remember, that's 45,000 cents, right? So that's actually $450 a day in profit. That's from just running the new one. If we're running just the old one, 800 gallons a day, we make $48,000. 48,000 cents, which is $480. So just running the old one, right, we get much less of it, but the profit margin is so much bigger. Right? It's 3 times as big, but you actually make more money. And then finally, what about the third one? X equals 475, y equals 1300. Our profit is 54,500 cents, which is $545. That's our maximum. So, these particular people, how many gallons of the chemical should be produced? They should produce 475 via the old process, 1,300 via the new process, and then make $545. And that is the last video of the semester, the end of the new material.